How is fracture toughness measured using destructive testing? Imagine a tiny crack in a metal part suddenly growing and causing a machine to break down. How do engineers figure out how resistant a material is to such cracks? That's where fracture toughness measurement comes into play. In destructive testing, a sample of the material is prepared with a small, sharp notch or crack. This notch is made carefully, often using precise machining or by applying repeated stress until a crack forms. The goal is to create a controlled flaw that can be studied. Once the sample is ready, it is placed in a testing machine that applies a steadily increasing load. The load is usually pulled apart in a way that stresses the crack tip, often in a mode called mode I, where the crack opens like a zipper. Sometimes, other modes involving shear forces are used, but opening mode is most common. As the load increases, the stress at the crack tip gets higher. The key moment is when the crack starts to grow rapidly, leading to the failure of the specimen. The machine records the exact load at this point. This critical load is essential because it shows how much force the material can handle before the crack propagates. From this data, engineers calculate the fracture toughness, which is a measure of the material's resistance to crack growth. They do this by considering the shape and size of the specimen, the crack length, and the critical load. One important value derived is called the stress intensity factor, which indicates the stress level near the crack tip at failure. Other parameters include crack tip opening displacement, which measures how much the crack opens, and the J integral, which relates to the energy needed to grow the crack. Common specimens used in these tests include compact tension samples and single-edge notched bend samples. These are designed to give consistent, reliable data. The testing follows standards like ASTM E1820 and ISO 12135, which ensure results are comparable across different labs and materials. Understanding how materials behave when flaws are present helps predict whether a crack will stay stable or cause sudden failure. This knowledge is vital in industries like aerospace, automotive, and construction, where safety is a top priority. By performing these tests, failure analysts can determine if a material was weak or if external factors caused the break. It helps prevent future failures and guides engineers in choosing the right materials for demanding environments. So, in simple terms, measuring fracture toughness through destructive testing involves carefully preparing a sample, applying controlled loads until it breaks, and then analyzing the data to see how tough the material really is against cracks.